Okay, I hope all of you ready because you want to have a long line of questions at the end of the talk. Why don't we begin? Hello again, everyone. Hello. It is our honor to introduce our next distinguished speaker, Professor Hitoshi Murayama. Professor Murayama is a leading figure in the world of theoretical physics, currently serving as a professor at the University of California, Berkeley. Many of you might have known him from his previous title as the director of the Kavli Institute for the Physics and Mathematics of the Universe at the University of Tokyo, or Todai. His work spans the realm of particle physics and cosmology, where he has made profound contributions. Notably, he played a part in the CAMLAN anti-neutrino detection experiment. He is also recognized for his discovery of anomaly-mediated supersymmetry breaking, a significant advancement in understanding quantum mechanics. As a recognition of his impactful contributions to physics and cosmology, he has received numerous accolades, including the 2016 Breakthrough Prize and the 2018 Humboldt Research Award. And now, he's ready to tell us more about the story of the universe. Please join us in giving a very warm welcome to Professor Hitoshi Murayama.
Okay, thank you. Good morning. And it looks like everybody's really enjoying this Asian Science Camp. That's wonderful. And all the lectures I've listened to have been fantastic. So we will see if I can live up to the level, same standard. So my talk today is very simple. It's meant to be introduction to cosmology. And cosmology, as the word said, is meant to be a study of the cosmos, namely the universe. And I got attracted to this field for a very, very simple reason, like any physicist actually have gone through at one moment. So if you look at the night sky, it's so beautiful. You're staring at the universe. And every little child, when I was myself, and still today, get attracted to ask very, very simple and profound questions about it. So how does this big universe begin? What is its fate? Where it's going? What it's made of? What are its basic laws? And why do we exist in it? So these are the kind of questions that humanity has been asking for millennia, like where do we come from? And now we can ask these questions in scientific terms. And that is something I find very, very exciting. So this kind of question, where do we come from, has been a question being asked in religion for many thousands of years, also in philosophy. And only like at the end of the 19th century, we start to ask this question a little bit more in scientific terms, like in evolutionary biology, that we actually came from apes. And I'm a little worried that the evolution may not be going the right direction these days, but no, don't worry about that. But the point here is that I would like to understand where we came from. What are our roots? Who we are? And so that kind of question is in some sense somewhat philosophical, but as I said already, it is really becoming a scientific question today. And to answer this kind of question, what we need is a machine that looks like this. Time machine. Unfortunately, we can't build this machine. It's against the laws of physics. We can't do that. But there are other machines that really act as if they are time machines. So one of the machines we use is these giant telescopes. So this is the picture of what is called the Subaru telescope, which Japanese astronomy community built in the big island of Hawaii atop the volcano called Mauna Kea, sitting at the 4,200 meters at altitude. And so this telescope actually houses a huge mirror whose diameter is 8.2 meters. So that actually goes through the roof of this room right here. So it's a huge mirror. And the reason why we would like to use this huge mirror for a telescope is because you would like to cast a big net to collect a lot of light, or photons rather. And if you can collect a lot of light, you can see very dim objects. And dim objects tend to be very far away from us. So using this kind of giant telescopes, you can observe galaxies like 10 billion light years away from us. And then you are looking into the universe as if they were 10 billion years ago. So you can literally look back into the past, and that's what I mean, that they really act like a time machine. But as I will also tell you in a couple of minutes, if you actually keep looking farther and farther away, try to understand how the universe was like earlier and earlier on, it turns out that there is a fundamental limit. You can't see beyond. And if you cannot see the universe beyond some point, the only thing you can do is try to do it. You try to do how it was when the universe was young. And for that purpose, we are using another kind of machine called particle accelerator. And I will tell you more about that also in a moment. So before getting into this, just to get an idea of what it means that using these giant telescopes, you can look back into the past, I'd like to give you some examples. For example, on the Subaru telescope, our team built a new digital camera. And the digital camera you might have on a cell phone may have, let's say, 10 million pixels. But the camera we built has 9 billion pixels. And it weighs 3 tons, so you can't carry on a cell phone. But using this giant digital camera, we took a picture, this is one of the first pictures we took, of the Andromeda Galaxy. Andromeda Galaxy is about 2.5 million light years away from us. So what happens if you can think of an alien living in the Andromeda Galaxy, and if they are pointing a telescope at our planet, trying to see what kind of creatures live on this planet, you will look to them like this. This is how you look like 2.5 million years ago. So 2.5 million years sounds like a long time for us, but it turns out that it's just a neighbor in this big universe. So it turns out that Andromeda Galaxy and our galaxy are actually being pulled towards each other because of the gravitational pull. We can see that Andromeda is pulling us, and eventually we are going to merge and clash on each other. And that sounds a little scary. If galaxies actually smash against each other, what would happen to us? But it turns out that when the galaxies clash against each other, it's a good thing. The reason being that if you leave a galaxy left alone, like Andromeda or our galaxy, it turns out the galaxies today are aging. And we heard about the aging population yesterday. And it turns out the galaxy is aging too. But when the galaxies actually collide and merge, then all the gas inside galaxy gets stirred up, and that would actually lead to the birth of new stars. So galaxy becomes young again. So if you look at this animation, you see the Andromeda Galaxy up here in a small patch, but as it comes closer and closer to us, at some point it starts to actually clash against the Milky Way, that's what galaxy is, and eventually form a single very big galaxy at the end of this collision. And so we actually merge together to become a more mature and round galaxy. And as you can see in this animation, the night sky looks even brighter after this merger because there are so many new stars born after the merger of two galaxies. So you should really look forward to this kind of event, especially that you are young. You just need to wait a little like 6 billion years to see this event, okay? So this is what happens from this point on. And so if you have the mergers of galaxies, that will stir up gas, and that will lead to the birth of many new stars. Now, if you look at this picture, and this is a picture of what is called the cluster of galaxies. So each of these round yellow objects are galaxies on their own. Each one of them might house like 100 billion stars on its own. And here you see about 100 galaxies are living together. So you might think of this like a New York or something. It's a big metropolis. It's a very crowded area of the universe. And this cluster of galaxies is actually at 2.1 billion light years away from us. So once again, if you think about an alien living in this cluster of galaxies, pointing a telescope at our planet, and how you will look to them is still a single cellular organisms. So this is the way you can look back into the past. So only when the light was emitted at this faraway galaxy, say 2 billion years ago, what you gets into the eye, or in the telescope rather, is the picture of this galaxy 2 billion years ago. So this is the way giant telescopes have been really helping us to understand how universe was born and how it's evolved to date. And if you could keep looking farther away, so recently you might have seen some of the news coming out of this James Webb Space Telescope, and they have been producing wonderful images using infrared light, not the visible light, of the faraway objects. And so this is one of such pictures. And if you blow up some of these regions, you see actually far away galaxies. And one of them, particularly this one, is really far away. So this particular one is 13.5 billion light years away from us. And you might have heard that our universe also has its age of 13.8 billion years. So what it means is that what this galaxy looks like to us is the picture of the universe when it was 13.5 billion years ago. So in other words, this is the picture of the universe when the universe was only 300 million years old. So this is a picture of a very young galaxy. And it's actually interesting. If you look at these pictures of very early young galaxies, they are still small because they haven't gone through this merger history. And they are a little irregular. And they actually become more and more mature as they go through the series of acquisitions and mergers. It sounds like companies, but early on, they looked a little irregular. So this is maybe a message for young people here, because you don't need to be mature and round. You can be irregular and have your own strength on your own, and in clash against people, that's totally okay. But anyway, this is the way early galaxies look like. And if there were an alien living in this early galaxy and point the telescope at a planet, what are they going to see? Well, nothing, because our solar system wasn't born yet. So this is how we have been able to understand how universe looked like early on by using giant telescopes. But it turns out that there's a limit to it. So I told you already that our universe is 13.8 billion years old. So now you know, if you try very hard and try to look 13.8 billion light years away from us, you should be able to see the beginning of the universe, right? And in fact, you can do that, and you can take the picture of the beginning of the universe and Big Bang. This is a picture of the Big Bang. So what's going on here is by using a telescope put on a satellite, they try to look 13.8 billion light years away from us in this direction, and you can see the glow of a hot and small universe in that direction. But if you point telescope in this direction, you also see the Big Bang. And there you see, there's a Big Bang happening. Over there too. And so we are living in a ball surrounded by the glow of the Big Bang. And you try to stretch out this ball to put that on this two-dimensional slide. So universe is not elliptic, as this picture suggests, but it is just that we are trying to draw a three-dimensional ball on a two-dimensional slide, and that's why it looks elliptical on this slide. And this picture is actually showing a little bit hot part or dense part of the universe, and a little bit colder and a little less dense part of the universe in an extremely exaggerated way. So this variation in density from somewhere is slightly dense and somewhat slightly less dense is only 1 part in 10 to the 5. But nonetheless, we can see the picture of the Big Bang today. So Big Bang is not just a story, something you see in front of your eyes. And this picture was actually taken by my colleague in Berkeley named George Smoot, who is at the top of this slide, working together with John Mather from NASA. And this is the way we know that 13.8 billion light years away, you can observe the Big Bang, which happened 13 billion years ago. So we can literally see the Big Bang. And George Smoot, I will show you some video about George Smoot later on. And he is a little funny guy. And so when he received this phone call from Stockholm that he's going to receive the Nobel Prize for this taking a picture of the Big Bang for the first time, and first thing he was being mad because in California, the phone call from Stockholm comes like 2 o'clock in the morning. So he was sleeping in bed. He was woken up because his cell phone rang. And it's very mysterious that Nobel Committee somehow figured out what his cell phone number was. So they are like CIA, I guess. And he got woken up by the call. So he was at the beginning, oh, who called me at this late in the evening? And he was mad. And then he listened and he said, okay, we're in Stockholm. There's a Nobel Committee. Oh, I'm going to get a Nobel Prize. And he started to become happier. Then he started to think about, okay, so that's a great news. So there must be something good about it today. And it turns out that in campus of the University of California, Berkeley, it's actually in a big city. So on campus, there are very few parking lots, except for those people who have Nobel Prizes. It says NL, Nobel Laureate. So you see parking lots for Nobel laureates lined up there. So he immediately thought about this and said, okay, now I can park my car on one of these parking lots. And he did that. Normally, he actually walks to the campus, but on that day, he intentionally drove to the campus, parked his car on one of these parking lots, and he got a ticket for it. Because technically, he hadn't received the Nobel Prize yet. All he had was a phone call. He hadn't gone to Stockholm to retrieve the prize. So he actually ended up paying the fine, penalty. So poor George. But anyway, so this discovery got me really fascinated. This happened right after I got my PhD. So as a result, I decided to go to Berkeley and to be together with George as a colleague to each other, and started to actually think more about how universe got started. Why do we exist today? And so I also got involved in many of the public outreach projects. I worked with a TV station in Japan called NHK to produce many shows. So to show to the audience what the Big Bang might be like, I actually came to Thailand once and filmed a TV show in Chiang Mai where they have this event of flying lanterns into the air. So this is how it looked like in TV show. So this is actually kind of hot air balloon. It was really hot to hold this in my hand. But the idea is that hot air brings all these lanterns up into the air. And the way they sort of go up is meant to represent the universe started with the Big Bang and started to expand and became bigger and bigger. So that is what this image was meant to convey. And since that time, the picture of the Big Bang got a lot better. So this is the latest picture we, humanity, managed to take of the Big Bang. So you can see the resolution is much, much better than the version George took. That was back in 1993. And this is the picture we now have from the measurement in 2017. So it's a much more recent picture we have managed to take from the Big Bang. Once again, it is extremely exaggerated between a slightly denser part of the universe and slightly less dense part of the universe. So if you actually sort of naively look at the picture of the Big Bang, it will look extremely boring. No matter which way you look, it looks pretty much the same. And another thing we learned from this is that, well, I told you this is a picture of the Big Bang, but I cheated a little bit. It's not the picture of the very beginning of the universe, but it's the picture of the surface of the Big Bang. And what I mean by this is that just imagine you look at the sun, and don't do that because that would burn your retina, but just think about looking at the sun. And sun is a ball of hot, dense gas, and light cannot go into it, right? So all you can see is the surface of the sun. In the same way, we are trying to look back into the beginning of the universe by looking farther and farther away using telescopes. But as you go farther and farther away, you are looking at the universe further and further back in time, and the universe becomes smaller and dense and hot. At some point, photon, light, cannot go through it anymore. So we are looking at the surface of the Big Bang. Beyond this surface, the universe was filled with hot, dense gas. So it was actually like a soup of elementary particles back then. So this is actually the limit, how far we can look with any telescopes we can ever build. So if you think about the history of the universe, this is where the universe was born for some reason. We still don't understand why. And it started to expand. And the picture of the Big Bang you have seen actually corresponds to this point when the universe was already 380,000 years old. And 380 years sounds like a very long time, but for the universe, 13.8 billion years old, this was really a baby picture of the universe. So it's a really amazing accomplishment by human beings that we managed to take the picture of the baby universe we live in. So that's really amazing. But just like the human baby, and I'm sure there are people who are much more expertise myself about how human the beings evolve. So when you think of the universe starting with the fertilized egg, and that starts to hatch into and divide in cells, and cells keep dividing. At some point, it actually becomes something like, it looks like a fish, has a grills, some point it has a tail, and eventually it goes through this, the sequence of evolution we've been through, and form a round face, round eyes, and the limbs, the arms and legs, and eventually become really human-like, and then the baby is born. So that is the moment that looks sort of like here, which is the farthest you can look back in time. And once baby is born, you can really observe the baby and study how the babies actually grow up into toddlers, and then to child, and to a teenager, and eventually to a grown-up adult. And of course, the growth becomes more and more slow as time goes on. But before the baby was born, so many things happened, as I just talked about. And all of these things have been very important to understand how human beings come to be. So a lot of important things probably happened beyond this wall you can ever observe. And that gives us a problem. If you can't observe the universe anymore beyond a certain point, how do you study that? And that's when what I mentioned earlier would come back, namely that if you cannot observe the universe early on, what you can try to do is to do it. Try to do what happened in the earliest moments of the universe in the laboratory somehow. And indeed, what we can do is to study the universe and do what was going on back then when the universe was only 3 minutes old using the machine called particle accelerators. So when the universe was only 3 minutes old, it was so hot that everything was moving so fast. And the stars couldn't exist, was broken down to atoms. Atoms couldn't exist either, it was broken down to electrons and nuclei. And nuclei were also broken down to protons and neutrons. So try to mimicking what was going on back then, we can throw neutrons against protons to each other in the laboratory. And then you can observe that once in a while, they actually stick with each other to form helium nucleus. And now that you have measured how often this happens, you can predict how much of the helium had been made in this hot Big Bang. And the prediction turns out to be the helium was made in the Big Bang with 3-to-1 ratio to hydrogen. And that's something you can actually test by observing the night sky, try to measure amount of hydrogen and helium in the universe today. And that measurement really turns out to be 3-to-1. So what this is telling us is that the kind of experiment that you can do in laboratory is exactly what happened in the earliest moments of the universe. It was when universe was only minutes old. So this is the way we can do the universe to study what was going on in its earliest moments. So that's the way we study the universe. You observe, and that's a great way of doing that. And you can go back to the moment when you see the surface of the Big Bang. But beyond that point, try to see what even the earlier moments of the Big Bang. You have to resort to other methods like using particle accelerator. So now we start asking the question, where do we come from? The first question is, you are made of atoms, right? And you have a lot of carbon in your body. You have calcium in your bone. You have iron in your blood. So the first question is, where do they come from? Where did the chemical elements come from? So if you look at this periodic table you see in any classroom, what I told you already is that hydrogen and helium were indeed born in the Big Bang. And together with a little bit of lithium, which you have actually in your cell phone in lithium-ion battery. So hydrogen, helium, lithium came from the Big Bang. But because you can actually do the universe in the laboratory, you can also tell that no further elements had been made in the Big Bang from beryllium and on. So no carbon, no oxygen, no calcium, no you, right? So you didn't come from the Big Bang somehow. So where did you come from then? So what is made in Big Bang is only the three first elements. Beyond that, they didn't come from Big Bang. But in the laboratory, you can again throw, say, 3 helium atoms against each other, and you can see that they can form carbon. But this happens so rarely that it should not have really happened in the Big Bang itself. It must have happened somewhere else. And now we know that this kind of reaction actually happened inside stars. And I tell you why we know that. So if you think of a star, the star we are most familiar with is, of course, our sun. And you might have heard already in the physics class in high school that the sun is powered by the process called nuclear fusion. So what's going on here is that you bring 4 hydrogen atoms together, made of protons, and inside the core of the sun, they stick with each other and form helium, just like what happened in the Big Bang itself. But now you have a problem because you start with 4 positively charged protons, and helium has only 2 positive charges. So to conserve the electrical charges, you need to spit out 2 positive charges, which come in the form of antimatter. And antimatter is not science fiction. They really do exist. So in this case, this is an antimatter of electron. Because electron has negative charge, its antimatter counterpart called positron has a positive charge. So this is how you can conserve the electrical charges in this reaction. But it turns out that this is not the complete reaction. You also need to speed up 2 additional particles, very ghostly shy particles called neutrinos. And Dr. Wan yesterday talked about the neutrinos in his experiment. And so these neutrinos are born inside the sun as well. And the way this reaction helps us understand it is to how the sun shines is based on this equation by Einstein, E = mc squared. So if you put this reaction on a scale, you see that the amount of mass you have before the reaction is heavier than the amount of mass after the reaction that's lighter. And normally, you don't think such a thing is possible. If you think about the big car accident, the 2 cars clash against each other, you see a lot of debris on the street. But if the policeman comes and collects all the debris and weigh it together, of course they are supposed to weigh just exactly as much as masses of 2 cars combined. So I remember learning this in elementary school. It's called the conservation law of mass. But that's actually not true. And that's what Einstein told us. The mass can be lost from the initial set to the final set of particles. And amount of mass that had been lost can be converted into energy, and that's how the sun shines. And in fact, if you do a little math, knowing how much light sun is emitting every second, so that is actually coming from shedding the mass of the sun. So it turns out that the sun is getting lighter by 4 million tons every second. It's a huge amount of mass. But the sun is even much heavier than that, so it can keep shedding 4 million tons of mass every second to give us this light and heat that we can happily live on a planet. So the sun is literally shedding its weight for us to be living on this planet. So that's the idea how the sun shines. But how do we know that? Well, this byproduct of this reaction, neutrinos, actually help us to understand this. Because I told you already, you can never observe what's going on at the center of the sun by looking at it, because light doesn't get through it. All you can see is the surface of the sun. But these neutrinos are so shy that they can get out of the sun without any problems. They just stream straight out from the center of the sun all the way to our planet. And they can also stream through this concrete of this building without any problems too. So it turns out, if you do the math, it's about 100 trillion neutrinos are going to your body every second coming from the sun. So you are actually exposed to this huge wind of neutrinos coming from the sun. Does any of you feel that? There's a wind of neutrinos coming from the sun? Whenever I ask this question in the United States, Americans raise their hand. But no Asians do. Okay, you do. Okay, thank you so much. So the idea is that this many neutrinos are coming from the sun, but at least vast majority of you don't feel it because it interacts so little with us. So, but what best you can do is possibly make a very big target so that you may be able to capture some of them. And Professor Kajita will talk more about this experiment tomorrow. It's called Super Kamiokande experiment in Japan. And this is a water tank that has the 50,000 tons of water in it. It's about 40 meters high, 40 meters wide. And what you can see in this picture is that you have all of these devices that are meant to collect light and detect individual photons, and it's called the photomultiplier tubes. And what you also see is the poor graduate students working in this experiment on a little rubber shaft. And to be able to observe neutrinos that give you a very, very faint signal, you need to avoid all kind of noise coming from radioactive material or dust inside this water tank. And Ifan Wan yesterday already talked about how pure you need to make a big device which has been building. So these graduate students here actually cleaning the tank by having a cloth and a spray of alcohol, swish, 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 and then you wipe the surface of individual phototubes in this picture, and you clean it very thoroughly, clean it, and then you go around the entire tank, and then you pour more water into it so that you can go one step up and repeat the process. And it takes a long time. It turns out to fill the entire tank, which is 40 meters high, it takes about 3 months to complete the job. So it's a big deal. But you can appreciate how big a target this is. And using this big target, you can observe neutrinos. But still, not that many. So using this huge tank with so many neutrinos coming from the sun, you can see about 15 of them every day. But if you have any experience trying to take a picture of a star, which is dim, it takes a long exposure so that you can collect enough light to take the picture of the star or maybe galaxy. So in the same way, if only thing you can see is only 15 neutrinos a day, you have to keep the exposure open up to 5 years so that you can take a picture of the sun. So this water tank is 1 kilometer underground. No light comes in there in pitch darkness, but neutrinos do come in. And this is a picture of the sun taken using neutrinos. And it's actually a picture of the center of the neutrinos where this nuclear reaction is happening. So this is how we know our sun is building atoms. But it hasn't solved the problem where you came from yet. Because sun is not a very big star, it can make atoms up to carbon, maybe oxygen, but definitely not calcium or iron. And moreover, if the atoms built in the core of the sun stay there, you can't use it, right? Somehow you need to take them out. To take them out, what you need is the star to explode. And this is a picture of a star that exploded in a suburb of a galaxy called Large Magellanic Cloud. And when a star explodes at the end of its life, single star may become as bright as the entire galaxy. And this kind of event is called supernova, because nova means a new star. And in the old days, people could actually observe this kind of explosion of a star in our galaxy in broad daylight, because so bright, you could see it during the day. So then you think like, okay, there's now a new star, and that's why people call it a nova. But it's so bright, people put super on top of it, and what's kind of explosion called supernova. It doesn't happen very often, maybe once in a century in our galaxy. So you don't want to miss the chance. It turns out, though, is that when this star exploded in this nearby Large Magellanic Cloud, this reaction went all the way up to iron and released so many neutrinos, and some of these neutrinos actually made their way into our planet and have been detected. So this experiment is the predecessor of Super Kamiokande. So it didn't have super on it. It was the Kamiokande experiment. But it was already pretty big, had 3,000 tons of water in it. And using this device, they managed to actually detect neutrinos coming from the explosion of the star. So I kept emphasizing that neutrinos are very shy. So most of the time, all you see is the noise. So if you think of the old analog radio, you may listen to this hiss. Shh. That's a noise, white noise in radio. But at one point, you see a bunch of neutrinos coming together in a big burst. And this burst was emitted when the star exploded 160,000 light years away from us. And even though this is a burst of neutrinos, what they could measure was only 11 of them. But at least it's clear that something explosive happened at this moment. And eventually, the astronomers confirmed that this actually came from this supernova, exploding star. So as a result, the Masatoshi Koshiba, actually who started this Asian science camp, received the Nobel Prize for this major work. And this is an incredible accomplishment. So I already mentioned this noise that might actually be a problem for this observation. So if this noise was too high, then even the burst of neutrinos might not have been seen or heard. And they had a lot of problem trying to reduce the noise level down, so they became ready for this observation only a month before this important event. On the other hand, a month after this event, Koshiba had a mandatory retirement, so he had only 2 months of opportunities, and the star exploded exactly 160,000 years before this moment so that he could receive a Nobel Prize. So one thing you need to know is that you need to be very lucky to be able to do a good job in science. But what we learned from this event is that this faraway star, you can never go there and see it really, but can actually produce many atoms. The the stars do build bigger and bigger atoms. And that's something we have learned from this event. So what we have learned so far is that when universe started with the Big Bang, it could make hydrogen and helium, just a little bit of lithium. So the first stars were born with only hydrogen and helium, basically. But as the stars keep shining, they start to build bigger and bigger atoms at their core, building up to carbon and oxygen and so on and so forth. And then that star exploded. And the elements like carbon and oxygen became dust, drifted in space for a long time, but eventually they got accumulated by pull of gravity, and that will lead to the birth of the second generation of stars. And the second generation of stars also kept shining and built bigger and bigger atoms, building carbon and calcium and iron. And then they exploded and spit out all these elements as dust in space once again. And that dust got accumulated by the force of gravity and led to the grandchild of the original star. So it is believed that our sun is the third generation. So when sun was formed, all the gas got put together by gravity and start to form the sun, but there was so much dust around it, and dust kept circulating around the sun at its birth, and the dust kept hitting each other. Sometimes they stick with each other and grew bigger and bigger, and eventually became a piece of rock, and that's what we are standing on right now. It's called planet Earth. So in this piece of rock, there was already enough of carbon, oxygen, calcium, and iron so that your body could be assembled from this dust originally that formulated the planet. So we came from the explosion of these stars. So the first question we ask, where do we come from? The answer is that you came from stars that exploded billions of years ago. So you are literally stardust. So that's the first answer we got about this question. And in fact, we can still observe the star that exploded a while ago. And this star was known to have exploded back in 1054 because an ancient manuscript in China and Japan that actually talked about seeing this star in the broad daylight. So we know when that happened. And at the core of this exploding envelope, you can't see it, what's going on inside using the usual light, but using X-ray, you can see what's going on inside, just like you take the X-ray picture in hospitals. And you can observe that there's something that's left over at the center, which is very, very dense. And that object is still spewing gas into space. And that is what became dust, eventually forms the next generation of stars in it. And this core left over is incredibly dense. Just imagine squeezing the entire mass of the sun down to this campus. It's as dense as that. If you can scoop up a little bit of this star called neutron star, then one spoonful would weigh as much as 10 million tons. It's an incredibly dense object that is left over after the star exploded in supernova. So here's one little life lesson. So there are all kinds of different stars in the universe. Some of them very light, some of them very heavy. Light ones tend to live long. So they actually undergo a long and frugal life. They may live up to even 100 billion years. But heavy stars, they actually undergo a very fast life. So they live fast and die young, and they live only maybe up to 10 million years or so. So this is a variation of different lives among the stars. So again, you can think about how you would like to design your life looking at this data on how stars actually end up dying. So okay, anyway, so this was great. At least we understood something, and that we came from stars that actually built elements up to iron. But it doesn't fully answer the question yet. So once you go beyond iron, the nucleus has so much positive electric charge if you try to squeeze them together, they repel so strongly, and you cannot actually fuse them together anymore. So it's known that no elements above iron could be born even in this exploding supernovae. But we need heavier elements too. Iodine may be important for thyroid in your body. Some people might care some other elements more than thyroid, like silver, platinum, and gold. You might care about them. So where do they come from? And you may be surprised to hear that we didn't know the answer to this question until 8 years ago. It's a new discovery. And the idea is that I told you neutron stars are the leftover after the supernova explosion. They are very, very dense objects. In some cases, neutron stars orbit around each other. And those neutron stars would wobble space so much, and space goes in a wave, and called gravitational waves, and they actually start to spiral in, and eventually they merge into a single black hole. And when neutron stars merge, reaction goes even further, and that's when we believe that gold was made. But we didn't know if this was really true until very recently. So what happened in 2017 is that these two neutron stars orbiting around each other merged by wobbling space so much. And wobbling space is called gravitational wave, predicted by Einstein. And what the gravitational wave does is stretch and shrink space, and that propagates through the universe. And that's a very strange notion, but that's what happens in gravitational wave. And when this gravitational wave reached our planet Earth has done this. While the neutron stars are orbiting away from each other, it was very slow, and wobbling was not very much. But as they start to spiral in, it happens faster and faster with the higher frequencies. Wobbling becomes also bigger and bigger, so our planet expanded and shrank. But when the neutron stars merge, then what remains the black hole, and nothing will come out of it. Have you felt that? Well, here in this picture, it says the scale of effect vastly exaggerated. So what happened in this case is that the entire planet expanded and shrank only by about a thousandth of the size of an atom, 10 to the minus 11 centimeters. So it's a very, very tiny effect, and no wonder you didn't feel it. But somebody else felt it, and that is what's done by something called the gravitational wave detector, and the name of the experiment is called LIGO, and 2 of them exist in the United States today. So the idea is that you have a pipe of the vacuum, which is as long as 4 kilometers, and you take laser to go bounce back and forth inside this vacuum pipe. You do the same thing for another pipe in orthogonal direction. And when gravitational wave comes, it stretches one arm, it shrinks the other arm, so the arrival time of light going back from the mirror this way and that way would not be the same anymore, and you can detect that difference by the technique called the interferometer. So here's the idea. Laser is a wave, and you split it into 2 directions, and this laser wave gets bounced back by the mirror and come back the way it started. And you design it in such a way that 2 waves coming together would exactly cancel with each other, so you are not supposed to see any signal. But if this one pipe gets stretched, and the other pipe gets shrunk, then you see the arrival times change. So what was supposed to exactly cancel, no longer do, then you get some leftover light, which you can detect. And that's the way they could manage to see this tiny, tiny expansion and shrinking of space that came to our planet. And it so happens that the signal is about 100 hertz. And if your eardrum was incredibly sensitive, and that's the frequency range you might have been able to listen to. So if I convert the signal to sound, this is how it sounds to you. So hopefully the sound will come out. So at the beginning, all you hear is the noise. This is the noise. But eventually you start to hear very low sound. Then low sound starts to go up as the neutron starts spiraling into higher frequencies, and it starts sounding like whoop, whoop. And just listen carefully to that. Could you hear it? Whoop. Let me just play it once again. So this is the noise. And if you get used to it, I can already hear this low sound. It starts getting higher and higher. And that's the moment when gold was born. And according to some calculations, this event produced as much as 10 times the mass of the Earth for the gold. But of course, it gets spread out into space, so it's still a very precious element at the end of the day. But this is how we learned how elements bigger than iron had been made in the universe. And this is only one event. We have not seen something similar since then. So we don't quite know if this neutron star merger can explain all of the gold we have on the planet today. So we need to accumulate more data. And in fact, India is now building the exactly same kind of observatory so that we can actually look at these events from all parts of the world. 2 in the United States, 1 in Europe, 1 in Japan, and eventually 1 in India. So that becomes a worldwide network trying to look for this kind of neutron merger events in the future. So that's great. Now we went one step further, answering the question, where do we come from? And what we talked about so far is how the elements were born inside the star or by the merger of neutron stars. But the next question then is, how were the stars born? Otherwise, none of the things I talked about so far wouldn't have happened. But once you come to this level of question, then we don't know the answer to that yet. Because the way stars are born have to do with the mysterious type of matter called dark matter. So if you actually take a picture of the universe today in the form of jelly beans, atoms we are familiar with make up only 5% of it. And the rest is made of something we don't know yet, named dark matter and dark energy. I talked about dark energy at the camp yesterday. I don't have time to get into that today, unfortunately. But I'd like to spend some time talking about dark matter, because dark matter is actually the mother in the universe that actually formed stars so that we could actually be born later on. So why are we talking about this crazy idea that there are far more matter in the universe than atoms? And that goes again, what I learned back in elementary school. I was told everything is made of atoms, but that's not true. Pretty much everything in the universe is not made of atoms. And we start to learn about this by looking at where we are in the universe. And this is where we are, the solar system, which is 28,000 light years away from the center of a galaxy. And because we are not at the center of the galaxy, we are actually moving about the center at an incredible speed of something like 220 kilometers per second. So I guess you all drove from Bangkok airport, but using this speed, you can go back to the airport in 1.5 seconds. It's an incredibly fast speed. And then you start to worry about this. So if we are moving that fast, why do we get out of the galaxy? Something is pulling us so that we can stay inside. What could be pulling us? Well, of course, there are a bunch of stars in our galaxy. It's about 100 billion of them. And they must be pulling us by the force of gravity. But the stars are something you can observe in telescope. You can count them up. They estimate how much gravity there is. And it turns out that there's nowhere close to be enough. And here's the data. So if you remember what you learned about solar system in high school, as you go to a farther away planets, they are farther away from the sun, gravity is weaker, so they have to be evolving at a slower speed so that they can still bound to the sun. So farther away you go, you're supposed to go slower. But inside our galaxy, that's not happening. No matter how far you go, you seem to be moving about at about the same speed. And that can't be possible. Well, what this means is that, well, if you think the stars, they are the only source of gravity, you are supposed to go more and more slowly as you move out. But somebody needs to make up with the rest, and that is what we call dark matter. There must be some form of matter, because that's a source of gravity. But you don't see in telescope, and that's why we call it dark. So our galaxy, we used to think, is a collection of stars, but it's actually an ocean of dark matter in which the stars are sprinkled as a small minority. That's what our galaxy should really look like. And we see this evidence on the scale of galaxies, but we also see the evidence on the scale of cluster of galaxies I mentioned earlier. And if you look at this picture, which is this the big city made up of 100 galaxies living together, you can notice there's something really, really stretched out here. And also here, also over here. This is also very, very stretched out. This is a faint, but you also see something is really elongated. This one is also stretched out too. So what are they? It turns out that this is a picture of a faraway galaxy behind this cluster of galaxies. But the dark matter inside this cluster is fooling us so that they are playing tricks to make this faraway galaxy looks very, very much stretched out. And just to get an idea of what's going on here, so just imagine that you have this cluster of galaxies here. Here we are on a planet, and you're looking at this cluster of galaxies. But just imagine there's another galaxy along the line of sight. And then the light coming from this faraway galaxy gets bent by the force of gravity from dark matter. So this cluster of galaxies then acts like a magnifying glass. And on the edge of the magnifying glass, all the letters you might read in a book may look very distorted. So that's what's going on. So if you just imagine, for the sake of discussion, that there are many galaxies far away behind this cluster of galaxies flowing like a river. Only when a galaxy comes just right behind this cluster, they will look stretched out. But as they pass through it, eventually they will return to their original shapes because nothing happened to them. They are at totally different parts of the universe, at totally different distances. But they would look stretched out when they happen to be right behind this cluster. And that's actually great. Namely that if the dark matter can play tricks on you, then you can tell where the tricksters are and how many of them there are. So this is the way you can figure out the way the dark matter is in this picture. And this picture has one cluster of galaxies over here and another cluster of galaxies down here. And what's painted blue is where dark matter is, which you can figure out because they're playing tricks on you. And what's painted in pink is actually the ordinary gas that got heated up to something like 100,000 degrees Celsius, and they are emitting X-ray. And the problem in this picture is that in this cluster of galaxies, I told you already that dark matter is holding stuff together by their force of gravity, but the gas is away from dark matter. And that's also true in the other cluster of galaxies. The gas seems to be away from dark matter. So this picture turned out to be an aftermath of the collision of two clusters here at a speed of 4,500 kilometers per second. So when they collide, each cluster is the ocean of dark matter with the gas sprinkled inside. The gas is made of atoms. They are tiny, but they can still hit each other. So they get heated up and there's a friction, they slow down, but dark matter keeps moving as if nothing has happened. So this is how you know that cluster of galaxies is pretty much made of dark matter, and ordinary gas would hit each other, they would interact with each other, but dark matter doesn't interact with gas and doesn't seem to interact with the other cloud of dark matter either. So that's how we can understand this picture. And some of you asked me the question yesterday, how do we know the amount of dark matter in the universe if you don't get to see it? And my answer was that if you actually strike an object and if you listen to the sound, you can tell what it's made of. And this is the way we can, for example, see different sound waveforms coming from different instruments. And if you listen to your friends talking, you can tell who's speaking, right? You can tell them apart. So the waveform has a lot of information in it. It turns out that the picture of the Big Bang I mentioned earlier is showing what part is a little dense, what part is a little less dense. And this variation in density going through the air is nothing but the sound wave. So it turns out that in the early universe that was filled with a soup of elementary particles, there was sound wave already. You don't need to strike it. And by listening to this sound, you can tell what's inside. And this is the way you can do the two-dimensional Fourier transform to understand the form of the wave in it. And this form of the wave is going to really tell you what the universe was made of back then. And the conclusion is that there is about 5 times more dark matter than the ordinary atoms in the universe. But they played a very important role. I told you already that the universe started out pretty much bland and boring. Everywhere looked the same. But there's tiny variation of density at the level 1 part in 100,000. And where dark matter was a little dense, there was a force of gravity that put more dark matter into the region, and that becomes a little bit more dense. And then gravity becomes even stronger, puts more stuff in, becomes even more dense. And as it keeps doing it, you start to see the density contrast starts to grow. And when in the region where you have more dark matter, the ordinary gas gets pulled in. But I told you gas will interact with each other. They can emit light, cool down, and form stars and galaxies, and eventually you. So dark matter assembled stars. But in a computer simulation, you can also study the wrong kind of universe that doesn't have dark matter in it. And in that kind of universe, density contrast doesn't grow. Therefore, no stars, no galaxies, no you. So you wouldn't be here without dark matter. And that's why I said already that dark matter, I consider dark matter to be my mom, because she assembled us from the primordial gas. And our team at Kavli Institute in Japan have produced the largest three-dimensional map of dark matter, which is 8 billion light years deep and 1 billion light years across. In this huge volume, you can determine where you have dense dark matter cloud. And if you compare that to the density of galaxies, you can see is that where dark matter is dense, you are bound to find galaxies. Where dark matter is dense, you are bound to find galaxies. So you can literally see that galaxies were formed by dark matter. And now that I mentioned that you have this mysterious dark matter putting stuff together, that you might ask the question, oh, could it be black hole? I have heard something of a black hole that exists at the center of galaxy. And indeed, if you actually watch the motion of stars at the center of our own galaxy, and just focus on this particular one, you see this star starts to speed up, clearly being pulled by something, and then start to spin around very quickly in this hairpin curve. And that really shows that there's something very, very heavy down here. And you don't see anything in telescope, and that is actually a black hole. And this black hole sometimes starts to actually brighten up. And clearly, black hole itself doesn't shine, but what you see in this animation, or in a video rather, is that something is lighting up around the black hole. So this is the cloud of gas, unfortunate gas that happened to come nearby this black hole, then starts to get sucked into the black hole. Then there's a friction, they get heated up, and they emit light. This is sort of the last cry before they get sucked into the black hole, and that's what you observe today. And you can even tell the colors change as the cloud gets sucked in from blue to green to red, because as you get closer to the edge of the black hole, your time gets more and more slow, and as a result, the color of the light also gets redder and redder. So that's what black hole does on you. So from this data, you can tell that the mass of the black hole at the center of a galaxy is about 4 million times the sun. Okay, that sounds heavy. But what I told you earlier is that it's only 4 million, but our entire galaxy, which has 100 billion stars in it, doesn't have enough gravitational pull to keep our solar system inside. So 4 million times the sun is nowhere close to be able to explain why we can stay in our own galaxy. So there has to be a lot more than that. So that actually leads to a very fundamental question here. So dark matter doesn't seem to be black hole. We also look for many dim stars. They don't seem to account for dark matter either. And you will hear more about neutrinos tomorrow, but they turned out to be too light to explain dark matter either. So including mysterious objects like black hole and neutrinos, nothing we know of can explain dark matter. What could it be? And we don't know yet. And many people thought that they may be actually new particles called WIMP. So WIMP is kind of a monster version of neutrinos that can pass through our entire planet any problems, but much heavier versions of it. And WIMP stands for weakly interacting massive particles. Once again, with E equal mc squared, if you have enough energy, you can produce massive objects. And Big Bang had a huge energy. It could have made heavier particles than we have ever detected so far. And they are point-like particles produced in the early universe, and they are still left over in space today. So if this idea is right, there are millions of them going to your body every second. Not as many as neutrinos, but there seems to be quite a few of them around us. And following this idea is that if this was made in the early universe, maybe we can do it ourselves to make the dark matter particles. And that's where you can use these giant accelerators. One of them actually exists in Europe at CERN. So what you do is to circulate protons, the nucleus of hydrogen, in one direction and another direction, and smash them against each other. And the machine is inside this big tunnel. And when they collide, then you can try to detect everything that comes out of that collision. So basically, you're trying to do a little Big Bang in a laboratory. And this is how you might be able to do it. So you bring in protons together from both sides. They collide in the middle of this detector. And a lot of things come out of this little band. You try to detect them all to see what was going on in the earliest moments. Now you can tell what movie they had in mind. And they are very serious people, so they go all the way to actually do this. So the question is, can we really make it? And we haven't actually managed to do that so far. But the amazing thing about these high-energy particle accelerators is that they are colliding protons or electrons against each other. They are relatively light, microscopic particles like tricycles. But if you ride on tricycles incredibly hard to bring them up to very high speed and high energies, then using E equal mc squared, you can convert the energy of tricycle into mass, so that out of the collision of tricycles, you might actually get a plane and tank coming out. That's what we're trying to do. And if one of them turns out to be dark matter, you don't see it, but you see the plane go in the other direction, so there must be something coming out here, but you don't see it. So that's how you know you succeeded in creating an invisible particle in your experiment. And that is still going on, and they're now trying to bring up the intensity of the collision much better by almost 1 order of magnitude. And experiment keeps going for another more than 10 years or so, so we will see what we can discover. At the same time, now so far we have not seen a signal of it, and our community has been going through a sort of reflection. And the WIMP I talked about occupies this range of mass out of all possible mass of dark matter that spans over 80 orders of magnitude. And even when you talk about particles being dark matter, it may be actually lighter or heavier. Or it could be even much lighter particle, sometimes called axion. And if the particle is that light, they form some kind of wave propagating inside of a galaxy. Or I told you already that black hole doesn't seem to be dark matter. But if there's an exotic black hole, which is much lighter than the mass of the sun, maybe. So that's the kind of possibilities we are talking about. So it turns out that there are many possibilities we haven't seriously studied so far. So if you start actually getting to the work, maybe there's a low-hanging fruits, you get to discover them fairly soon. So the community now started to look very intensively over this entire mass range of dark matter. And of course, if you're trying to do this experimental search, you need theory for it too. So I've been working quite extensively, who used to be a postdoc in Berkeley, and now a professor at Hebrew University in Israel, Professor Yonit Hochberg, talking about all kinds of new possibilities on what dark matter may be. And one idea we had, the dark matter may be also similar to nucleus. It's a composite object, not elementary particles. And they may actually lead to different experimental and observational signals. So that's the kind of thing we are actually working on today. So we haven't answered this question yet. But if you do manage to understand and know what dark matter is, then we can start talking about the moment dark matter was born. That is likely to be much earlier moments than a minute where the helium was born. So we get to learn more about what was going on at a very early moment of the universe. So now we're getting closer and closer to the very beginning. And then the next thing I would like to tell you is that another particle, neutrinos, may also tell you about what was going on even at the earlier moments. And that has to do with the antimatter. So I told you already that antimatter does exist. So here's me. Here's anti-me. And actually, this is wrong. So if there were really antimatter version of myself, if you just look at them, you can't tell them apart. So if you make a mistake of shaking a hand with the antimatter person, you end up in a huge explosion. So you gotta be careful before you shake your hands. And what do you know in a laboratory experiment is that if you send in high energy enough, in this case, the gamma ray photon, and then the energy can turn into matter, but it always comes out to be one matter particle and one antimatter particle. This is the first antimatter particle created by human beings by Irene Joliot-Curie and her husband. So matter and antimatter can be made always one to one. Here's another experiment being done at my home, Berkeley, some time ago. And here they managed to create antiproton using this accelerator. And this antiproton comes into this photographic film. They would meet the proton counterpart, and antiproton and proton would annihilate one to one. And they turn into energy. Energy materialized into different particles over here is called star event because it looks like a star. But what you learn here is the matter and antimatter would annihilate one to one. They are made one to one. They annihilate one to one. And antimatter is really there. It's not science fiction. It is actually useful because I've been just through what's called a PET scan, where you can do a cancer diagnosis using antimatter, which is injected into your body. Because this antimatter material would accumulate to the place where the biological activity is very high. and then that material would emit antimatter that would quickly annihilate with matter around it and produces this high energy gamma rays, which you can detect in this kind of device. And then you can tell where cancer cells are. So this is actually something people use in hospitals these days. And in some movies, they actually get to use far more antimatter. In this movie, Angels and Demons, starred by Tom Hanks. And here's Tom Hanks. You can tell it's a pretty dramatic movie. And here's an experiment being done at CERN. And apparently in this movie, this is antimatter. It needs to be suspended. If antimatter touches the wall of this container, then they would annihilate with each other. You don't want to do that. And really surprising thing about this movie or the novel that was actually based on is that one scientist at CERN managed to create a 1/4 gram of antimatter without the knowledge of Director General, and that was put into this container that falls into wrong hands. And this is actually a problem if this happens, because just a 1/4 gram of antimatter, if that annihilates with matter around it, converts all of its mass into energy, and that energy would be equivalent to the atomic bomb in Hiroshima. You don't want to see that happen. And what's wrong with the story, though, is that 1/4 gram of antimatter had been created without the knowledge of Director General. To make this much antimatter, you need to play accelerator by a lot, and that consumes a lot of electrical power. That would take a lot of money. To make this much antimatter, you need to spend the power bill that goes up to billion, trillion dollars. And Director General didn't notice this. What kind of budget do they have? I don't get it. So the morale is very simple. Human beings can never, ever create this much antimatter to cause any problem. But the Big Bang did. And that's a problem. So it turns out to understand what happened in the Big Bang itself, we may need to know something a little bit more about this ghostly particle called neutrinos. So at the Big Bang, there was so much energy, and that turned into matter, always 1-to-1 with antimatter. So they were equal in their numbers. If we stayed that way, eventually matter and antimatter would meet, they would annihilate 1-to-1, and universe would have been empty, and you wouldn't be here either, right? So something must have happened. So somebody, at some point, somehow, picked up one antimatter out of a billion, somehow changed it into matter. So there's a little difference between the amount of antimatter and the matter. They will still meet and pretty much all annihilate with each other, but now there can be a leftover, and that's supposed to be you. So that must have happened at some point in the evolution since the Big Bang. And the only thing we can think of, a matter particle that can turn antimatter to matter, is neutrinos. Because if you think of a particle like electron, it has a negative electric charge. Its antimatter counterpart has a positive electric charge. Negative charge can never turn into positive charge, so they can't turn into each other. Neutrino is a matter particle, but has no electric charge, 0. Antineutrino has an electric charge -0. That's the same as 0. So that's why they can, in principle, turn to each other. And then the neutrinos could have taken one antimatter, turned that into matter, so that we could survive. We don't know if this is true yet, but because of the discovery you will hear about from Professor Kajita tomorrow, this story became far more plausible. So if this is right, that neutrinos actually saved you from the fate of a complete annihilation. And I'm not very good at editing graphics, so I spent hours changing I of Incredibles into new. But anyway, so they might have superheroes. And that's why Professor Kajita is now starting a new experiment trying to look for subtle difference between the behavior of neutrinos and antineutrinos. By mass producing them using particle accelerator and shoot them at a new experiment called hypercamiocande that's 8 times larger than already huge supercamiocande, so that possibly they may be able to see the difference between the behavior of neutrinos and antineutrinos. And it's a competition. And I skip some of that. There's another experiment being built in the United States. In this case, you're shooting the beam of neutrinos from Chicago, near Chicago, Illinois, to a mine in South Dakota over 1,300 kilometers, and we'll see what happens. The idea is very simple. When you produce neutrinos, let's say in strawberry flavor, they may start turning into half chocolate on its way, and eventually turn all into chocolate, and come back partially into strawberry, but you might also take a hint of a pistachio in it. And this is what you would like to measure. And you do the same experiment with antineutrinos, and ask the question if there's any difference between them. So that's how we hope to learn if the neutrinos really were the superheroes who saved us from complete annihilation. If we learn that, we get this much close to the Big Bang. Now, in the final 5 minutes, I'd like to tell you what we are learning about maybe the earliest possible moments of the universe called inflation. So dark matter may be our mom, neutrinos may be superheroes, inflation is our dad. So the idea is that universe, everywhere you look, looks pretty much the same. No matter how much you go, universe doesn't seem to change very much. And I told you about this also with a picture of the Big Bang. No matter where you look, universe looks pretty much the same. And that actually looks impossible. Because if you look 13.8 billion light years away from us, that part of the universe emitted light that just reached us. That light hasn't had time to reach the other end of the universe yet. But how do they know to have the same temperature? How did they arrange themselves without talking to each other? That sounds impossible. So the only reasonable explanation we came up with is that, okay, universe was at the beginning incredibly tiny, so that everybody could talk to each other. So they agreed what temperature they would eventually have. They got stretched enormously by a process called inflation that stretched out this tiny, tiny universe to a huge size instantly. And we heard about coronavirus earlier this morning, but inflation must have actually stretched out the size of coronavirus into a size of galaxy in an instant. There was an enormous expansion. And when the universe was so small, surely they could all talk to each other so that they have now the same temperature, which they still remember today. And that's the idea of inflation. But when the universe is so tiny, tiny space is governed by something called quantum physics. Quantum physics is really weird. Single particle can exist here and there at the same time. You can be no energy, plus positive energy, negative energy at the same time. Everything subject to uncertainty principle. Everything undergoes quantum fluctuations. So in a tiny universe, the universe itself was going through the quantum fluctuation, and energy comes in and out of empty space all the time. And that fluctuation eventually got burnt into space, and that's the picture of the Big Bang we talked about. And this tiny variation, which came from quantum fluctuations, had been nurtured and grown by dark matter into stars and galaxies. So that's why I said the inflation is kind of our dad, because inflation sowed the seeds. And they have been nurtured by our mom, dark matter, so that we could be born at the end of the day. And again, we don't know if this is true yet, but this is the best theory we have today. So if that's the case, we hope we can observe the moments when the whole universe was incredibly tiny. And when the universe is incredibly tiny, governed by quantum physics, even the space itself must have been fluctuating. And this fluctuating space would eventually become the gravitational wave you heard about before. And that gravitational wave can easily get through this thick soup of particles in the early universe. And that fluctuating space, wobbling space, can wobble also the light coming from the Big Bang. And if you observe that, and there's a plan for doing a satellite experiment called LIGHTBIRD by Japanese Space Agency, then we are, in principle, looking all the way back to the moment when the whole universe was smaller than the size of an atom. And that would be our ultimate root, our origin story, where we came from. So George, I mentioned earlier, put that together in this video, so I'd like to play it for you.
I really admired the band, and so when they said we wanted to react to Big Bang with the guys from your lab, I said, no way, I want the band.
And we can hear it.
So now I got to tell you what the Big Bang is so you guys can do this before the sun goes down. Okay, so the idea is everything in the early universe was packed together very densely. It may have gone for infinite. We don't have infinite people, so we just have to use what we got. And everything stretched, right? Everything got bigger. And the further away you are, the faster you go. So we're going to want to start at the beginning with everybody packed, dense, and jostling around and playing high tempo.
So here's the beginning of the universe.
Then at the mark,
this is
everybody
the Big
moves
Bang,
apart.
people running.
The people on the outside moving faster than the people on the inside. And there's a little bit of irregular motion.
That's
so
a quantum
miss some
fluctuation.
steps. Okay, I know you can do this. Right? And then what happens is you're going to coalesce together in groups of 6. Right? So you have to find 6 buddies. And half of you are going to form spiral galaxies. 3 people facing one way, 3 the other, and you rotate slowly as you move out. And the other half form elliptical galaxies,
So these are
which are
elliptical galaxies.
round blobs that keep moving out.
Here's a spiral
So,
galaxy.
Now, there's a brass section out there called tubas. They make a really spectacular spiral galaxies, a really big one, like our own galaxy or like Andromeda. So you guys get to be near the middle, and you get to make a really cool, you don't have to run out so fast, but you get to be able to orient where half is facing the other way, and you get to rotate with a sort of twist up. And you're like the centerpiece of this whole thing. Go tubas. Great, guys.
That's where we came from. So the idea here is that 80% of people here are dark matter. You don't see them. George himself is sitting at the center of the galaxy, so he's actually a massive black hole, 4 million times the mass of the sun. But this is the story we really would like to understand by more measurements and experiments, so that if this is the right story or not, did neutrinos really save us? Did inflation really happen? And that's the kind of research that is ongoing today, and hopefully you will join that as well. Now, lastly, the reason why actually doing and fascinated by this kind of science is also because that would provide a different perspective to me. And this is the picture taken by a space probe called Kaguya, launched by a Japanese space agency, that went around the moon. And when the probe is on the other side of the moon, that this object cannot see our planet. But as the probe starts to circling around the moon, our Earth starts to come up above horizon. And this is the video I was very moved by. It's called Earthrise instead of sunrise. And what you see here is clearly that our planet is just a tiny piece of rock. But it's so beautiful. And 8 billion people are living on this tiny piece of rock. We're fighting each other all the time, and we are really contaminating this beautiful piece of rock. If everybody looks at this picture, I hope they will see that, we have to help each other, and the whole world can work together. So that's the message. Thank you.
Thank you, Professor. Hold on. I don't think we have enough time for the question. Maybe only for a few.
I'm sorry.
I'm sorry about that. But Professor will hold a camp this afternoon. So right now, I think I'll let the speaker pick the question. Then, so
okay.
you can just take a seat and rest your
Okay,
hand.
sorry.
If
Please
you
come
look
to the camp and ask more questions.
Okay. Because we will have lunch with scientists as well, so we have to keep time. We can have a few questions if you want.
Okay. Can we have a few questions, he says? Maybe just a few.
So you can pick the lucky one.
Okay. Oh, wow. Just,
You can
just
raise your hand
start with
if you have
one, the
questions.
first one on this line.
So thank you for the opportunity, sir. I'm Aryan Saulagai from Nepal. My question to you is, do mergers of black hole also work on the same principle? What is the connection of antimatter relegation with it? And how are black holes connected with cosmic strings?
Yeah, so the matter and antimatter feels exactly the same gravity. So black hole cannot tell matter from antimatter. So black hole would treat them equally. So black hole cannot explain why there's more matter than antimatter in the universe today. So that's why we need to rely on something else that can tell matter from antimatter. And the neutrinos I mentioned is at least one candidate that might be able to do that.
Also, another question.
Only one question, I'm sorry. Maybe one on the other side?
Hi, sir. My name is Neha. I'm from India. So, first of all, thank you for the lecture. My question is, some scientific theory do suggest that multiple Big Bangs may exist. So, if they do exist, will this multiple Big Bang or universe affect our observable galaxies?
Yeah, so we really don't know what dark matter is. So some people speculated that our universe may be like a sheet of paper in a high dimensional space. There may be a stack of sheet of papers, and then we are living on one sheet. Dark matter may be stuck on the other sheet. Then we can never touch it because they're in different parts of the universe. Then we may never know what it is. So people did talk about the possibility. So what we learned from this example is that there's no guarantee we ever be able to meet dark matter. But at least we gotta try. I'd like to see my mom.
Thank you.
Okay, all right. This is a real cliffhanger. If you are interested, you are welcome to join the camp session held by Professor later.
Okay, see you later.